Okay, let's start with a do now. Try this problem. And you should pause the video now and try the problem because I'm about to show you my solution. Okay, pause it. Okay, so for this problem, first it says it's in equilibrium with this 3 kilogram mass and it's stretched 12 centimeters. So just knowing that, you can write a balanced force equation, solve for K, and get the spring constant, which is the same for the rest of the problem. So for the rest of the problem, it's the same spring, and now you put a different mass on it. The mass starts, it starts at a certain height, but you don't know how far down it is to equilibrium because it's a new equilibrium. So you have to find that new equilibrium, the stretch distance for the new equilibrium. Again, that's a balanced equation, and then solve for x, which is 16 centimeters. So that's from the starting point to equilibrium, 16 centimeters. But it's going to go through equilibrium and it's going to go in equal amplitude below equilibrium. So that's going to be 32 centimeters total. Okay, there's that problem. Okay, so today we're going to look at some different systems with more than one spring. So I'm calling them Masson spring systems 1 and 2, and there are actually 2 variations on the first one, A and B. And then I'm also going to talk about why we can ignore mg, the gravitational force in these spring systems, um, if we think about it a certain way. So we'll do that. So the first system looks like this, and it says at the front of the classroom, because normally I would set one up just like this with one of those green carts on the track, and 2 springs going to posts on either side, and this cart can oscillate back and forth like that. So the question is, what will be the frequency of oscillation if you know the 2 spring constants? And I'm telling you how to do this problem. We'll draw a free body diagram. We'll write an expression for the net force in the form F equals kx. And then we'll find what that effective k is, and we'll use the k to find the period and the frequency. Okay, let me show you this. Okay, so the free body diagram for this oscillating object that's oscillating left and right is here. It's got a force from this spring 1 that's pulling. Let's assume, okay, if this is equilibrium right here, but let's assume that the object is displaced a little bit to the right. Displaced to the right, so that's this one here. The force from this spring pulls it to the left, but the force from this spring, which is compressed, also pulls it to the left. And that's kind of a weird idea, but you've got K1x and K2x both in the same direction. When you write your net force equation, it's K1x plus K2x. In other words, K1 plus K2x. That's your effective K, and that's a new idea, effective K. And we can use that K. Once we know the K, we can substitute it in the period equation or to find frequency, and we can find the period just as long as we know that effective K. That's kind of an important big idea we'll use a lot in different, more complex systems. Okay, the next system we're going to look at is I call it system 1B. It's also 2 springs, but instead the mass is hanging from the 2 springs, so it would oscillate up and down like that, up and down. And for now, we'll just assume that these 2 springs have the same K, and we're going to do the same procedure that we did for the previous one. Here's system 1B, and you can see that in equilibrium, the 2 kx's are balanced by an mg, so you could say, or we're going to call it F naught. So an initial upward force, there are 2 of them up, 1 mg down, they're balanced. So the initial upward force, we're going to call it F naught, and it's equal to mg over 2. Then when it's displaced downward an extra distance, x, then the upward force is F naught plus kx for both of the springs. So that minus mg is the net force, and it's not balanced, but that's what the net force is. You notice I don't set it equal to anything. And then I have an equation that looks like net force equals, look at how these mg over 2's cancel with the mg, and so you just get 2kx. So that's an example of mg kind of going away there. And the effective k here is 2k, which is the same as what it was in the previous example. both of these are considered parallel systems. So that's parallel, and this is parallel. Now let's look at another system that's two springs in series. So the idea of series and parallel, one after the other is series, and next to each other, like parallel lines, is parallel. Okay, let's look at that example. Okay, so in this example, again, in equilibrium, the initial upward force is equal to mg, and so Fo equals mg. And then when it's displaced a distance x down, what's interesting is that each of the springs is only stretched by half of x, or x over 2. So you have Fo plus kx over 2 is the force exerted upward only by this spring, because this is the only one that's in contact with the mass. So that's the upward force. And so the net upward force, replacing Fo with mg, you can see again the mg's cancel out and you get k over 2x. So here the effective k is k over 2. And again, once you know the effective k, you can just plug it right into the equation for the period of a mass on a spring, 2 pi square root of m over the effective k, and that gives you the period. So hopefully you can see the pattern that when you have springs in parallel, their k's add. So I just did it with 2 springs, but for 2 springs the effective k was k plus k, or 2k. And it turns out they don't have to be the exact same k, they could be different k's and they still add. And for series, it's a little more complex. If there are only 2, it's 1/2. It's divided by 1 over, it's k over 2. But the more general equation for more than 2 is 1 over k equivalent, or k effective, equals 1 over k1 plus 1 over k2, etc. So just be careful, because this is 1 over k effective, and k effective is 1 over all of this. Okay, now I'm going to show you the last thing for today, which is why horizontal and vertical and inclined systems are equivalent when using simple harmonic motion equations, and why we can are equivalent to each other when using these equations, and why we can use F equals kx for displacement from equilibrium and ignore mg. And we kind of saw that already in some of the examples. Okay, here's an explanation I wrote up about why we can ignore mg when we write these equations for Newton's second law equations for a hanging mass on a spring. And so if you look at a mass on a spring at equilibrium, at that location, if you consider the stretch distance x1 from the unstretched location, then kx1 equals mg. That's balanced, and acceleration equals 0. But if it's displaced up an amount delta x, then the stretch from the unstretched location is kx1 minus delta x, right there. And so if including mg, including all this, being very, so I guess what I want to say is I'm doing this problem in a really meticulous way, starting from the unstretched length, just so that you can see that you can actually start from equilibrium and ignore mg. So these two terms cancel each other out, and you're left with k delta x equals ma for upward displacement, not including mg there. And then downward displacement, similarly, you've got mg down, and then kx1 plus delta x is the upward force, and the acceleration is upward. Again, these two terms cancel out, and again you get just k delta x equals ma. So this is just like a horizontal spring where F equals kx equals ma. And so you can really treat a vertical spring just like a horizontal spring, where the only force acting on it is kx, assuming that the force is measured from equilibrium, not from the unstretched length. So the conceptual way to think about it is that the force from gravity that we seem to be ignoring is canceled by the original stretch force from the unstretched to equilibrium position. And you can ignore them both and they cancel each other out. So there's your explanation of that one. And that's all for today, or for this, for these notes.